Okay, so let's start. Um, so in the last couple of classes, we were discussing algorithms for solving convex optimization problems. We started off with numerically trying to solve unconstrained minimization problems, and we saw sort of a general class of methods, the so-called descent methods, out of which gradient descent is one particular algorithm, and the other algorithm that we saw was Newton's method. So in gradient descent, so any general descent algorithm basically involves two things. One is from a given point, it's an iterative algorithm. So you move towards the minimum through a sequence of steps. At each step, you are at some point, and from that point, you decide to move in some particular direction with a given step size, according to a given step size. So to specify a descent algorithm, you need to specify how you choose the descent direction and how you choose the step size. In gradient descent, you choose the descent direction to typically be the negative of the gradient. And the step size can either be fixed to be a constant or it can vary with the iteration. The best, one of the most popular approaches of choosing the step size is using backtracking line search. In the previous class, we saw that if we actually use backtracking line search, then we converge much faster. Right? So that is one class of approaches, and this can be generalized to this method of steepest descent, wherein you choose the descent direction to basically solve this particular kind of optimization problem. And if in this case, if the norm is chosen to be the standard Euclidean norm, then it just reduces the standard gradient. But if you choose a different norm, then you get a class of other approaches. Right? So in general, you're always better off choosing some method of steepest descent, either Euclidean norm or L1 norm or some other. Okay. But we saw that we can obtain much faster convergence for convex optimization problems, for smooth convex optimization problems, provided that you know or and can compute the Hessian. And if you can, then the best thing you should do is try to solve using Newton's method. So, what is the basic idea behind Newton's method? At each step, you try to solve a quadratic optimization problem. Right? So you look at the second order Taylor series approximation of your function at the given point and try to solve that exactly. And that basically reduces to choosing the next step to be the current or choosing the next value of x, next point, to be equal to the current point plus some delta t times v star of xt minus 1, where this v star, the descent direction, is equal to the negative of the Hessian inverse times the gradient. And in that little example that we saw in the previous class, we could see that convergence was much faster. In fact, it converged in one step because we were dealing with a quadratic optimization problem. And the nice thing about the Newton's method was that you could very easily extend it to solve equality constraint minimization problems. Right? So suppose you have a problem of the form minimize f of x subject to a bunch of linear equality constraints, then all you need to do is you try to form the Lagrangian and try to solve this, and we saw that the Newton's method effectively boils down to solving a bunch of linear constraints. So our V star of xt is now a slightly bigger matrix inverse times this particular vector. Right? So ultimately these are all linear updates. Right? There is some kind of matrix multiplication and nothing more than that. So if you're able to compute the Hessian and the gradient some particular method, then you have closed form expressions for these, then you can always solve using Newton's method. Right? So all of this only allowed us to solve equality constraint minimization problems. So in today's class, we'll see how we can solve inequality constrained minimization problems. Okay. So the class of problems we want to solve are those which can be expressed in standard form. So we want to minimize some f0 of x subject to maybe some fi of x less than or equal to 0 and a times x equal to b. Right. So we want to solve problems in the form minimize some f0 of x subject to fi of x less than or equal to 0, I equal to 1, 2, 3 up to n. So we have n inequality constraints and a times x is equal to b. So we're only focusing on the class of convex optimization problems that can be expressed in the standard form. Right? Now another way of looking at this is the following. So we want to minimize this particular, we want to solve this constraint minimization problem. We do what we did in a previous class. We try to pose this as an unconstrained minimization problem with only, we try to get rid of the inequality constraints and only keep the equality constraints. So this is the same as saying we want to minimize f0 of x plus summation I equal to 1 to m I minus of fi of x subject to the constraint that ax is equal to b. Well, what is I minus of fi of x? Or I minus of z is defined as something which takes the value 0 if the constraint is satisfied, that is z is less than or equal to 0, that's equal to plus infinity upwards. So solving a solution to this unconstrained minimization problem or this minimization problem is the same as the solution to this constrained minimization problem. Okay, but I mean, we can't really solve this numerically because this function is not smooth. There's a sudden jump at z is equal to 0. Right? So the class of barrier methods try to basically approximate this particular function. Instead of I minus of z, let's replace it with some other function which is close to 0 for z less than or equal to 0. And it's very high, there's a sudden jump at z equal to 0. It doesn't matter if it's not defined for z greater than 0. Because we're only interested in the regime where z is less than or equal to 0. So the basic idea is you replace I minus of z with a barrier function. And the class of barrier functions that we will be interested in is the log barrier function. What is that? So you replace it with the negative 1 by t log of minus z. So I'll define this to be L t of z to be equal to minus 1 by t log negative of z. Let's just see what this looks like. let's say x is equal to, let me try to plot this from minus 10 to minus 0.001 in steps of 0.001. And so we plot this for different values of t. Minus 1 to say 10 in steps of 2. X 1 by t log of minus x. This is what it looks like. So this would be the curve for t equal to 1. It's nice and smooth. It's just minus log minus x. But as we increase t, we see that the curve becomes sharper. Right? So for t far away from 0, it's kind of flat, and for t very close to 0, it becomes sharp. Right? So the natural choice of function would be, if you wanted to best approximate I minus of z, then probably the best thing to do would be to just choose t to be something very large and try to solve using Newton's law. Right? But this ends up being a bit of a problem. If you choose t to be very large, then what would be the derivative or the gradient of this? At t close to 0, the gradient suddenly becomes close to infinite. And that can cause numerical stability issues. So instead, what you try to do is, you don't keep t to be a constant, you try to iterate through the t. You first choose with a suitability, maybe something close to 1, and then you keep increasing t in steps. So eventually what we want to get to is t being something large, because that's the only thing that is going to get you to close to the optimum. Right? But instead of directly choosing a t sufficiently large, you try to grow t step by step. Right? So let's define this function phi of x to be equal to summation I equal to 1 to n minus log of minus f of x. Okay, so this is the same as what I had previously without the 1 by t. So this is what I'll call the log barrier function for the problem. Right? So the closer each fi of x is to 0, the larger this is going to. So effectively what we want to do is try to solve for the minimum for all x such that a times x is equal to b. We do have equality constraints of f0 of x. Originally we just had f0 of x, we just wanted to minimize f0 of x, but instead we'll try to minimize t times f0 of x plus phi of x. So minimizing f0 of x plus 1 by t times phi of x is the same as minimizing t times f0 of x plus phi of x. And this just ensures that we don't run into too many numerical stability issues. Because now this phi of x does not depend on t, it's still nice and smooth. Right? Okay. So effectively, you can think of it in another way. So 1 by t times f of phi of x, as you increase t, the contribution of this keeps decreasing, right? Which was what we were aiming for. What this does is it increases the contribution due to f0 of x, by keeping the contribution of phi of x the same. The advantage of doing so is that the gradient of phi of x still remains the same, it doesn't change. You are only increasing the component of t times f0 of x. Okay? So we have phi of x. What would be the gradient of phi of x? This is the composition of functions. Minus, okay, summation I equal to n phi dash of x here. Sorry? So 1 by fi of x times the gradient of fi of x. Well, you actually have 1 by minus fi of x times the negative gradient of fi of x, which is just the same. So this is the gradient. What is the Hessian going to be equal to? Because we need this in Newton's method. Summation I equal to 1 to n. Yeah, so 1 by fi of x, Hessian of fi of x, the negative sign, plus 1 by fi square of x times gradient of fi of x. Gradient is a vector. So it should be gradient of fi of x. Gradient transpose, what are the dimensions of the gradient? Is it a row vector or a column vector? It's a column vector. And what does the Hessian have to be? Has to be a matrix. So what should this be equal to? What? The outer product of fi of the gradient with itself, or gradient of fi of x times gradient of fi of x transpose. Right? Okay, so now we know how to compute the gradient and the Hessian. So what would Newton's method for with the log barrier function look like? So the barrier method essentially does the following. So you start with initialize. Some x which satisfies the constraints. So it should satisfy ax equal to b, and it should satisfy all the inequality constraints with strict inequality. So fi of x should be strictly less than 0 for all x. So we start with some such x, and we'll define some parameter mu which is greater than 1 and some epsilon which is greater than 0. Okay, so we want to ensure that we are epsilon close to the actual constraint minimum. Right? So what do we do? So you run while we will see what the stopping condition should be. You do the following. So you run Newton's method. Starting at x. For the following optimization problem, for minimizing p times f0 of x, so we also have to initialize some p which is greater than 0. So you want to minimize p times f0 of x plus p of x subject to ax equal to b. Okay. You run this for a number of iterations, you fix t, and you run this for a number of iterations until you get something. Right? Call the output say x star of t. Okay? So you run Newton's method till it converges, and you call the output x star of t equals to one particular value of t. You next increment t. Okay. Set t to be equal to mu times t. Remember that mu is greater than 1. So multiplying by mu only increases the value of t. And you set x to be equal to x star of t. Okay, so now you are changing the objective function, right? And you are starting with a new initial point which is going to be the final point that you get from the previous iteration. Okay, and then you keep running this until some kind of stopping condition is reached. So this is essentially the barrier method. This is how it works. Now there are a couple of points here. One is I'm running Newton's method till it converges. But anyway what I get while running Newton's method is not the optimum value. Anyway it's far from the optimum. So why not just run a few rounds of the Newton's method, update and then run the outer method. And it turns out it doesn't make too much of a difference because Newton's method is very fast. Whether you run Newton's method up to convergence or not does not significantly change the performance of the algorithm. So that's point number one. Point number two is we need to choose a suitable increment, mu. How do we choose mu? We can choose mu to be something close to 1 or something much larger than 1. As it turns out, changing the value of mu does not significantly impact the performance of the algorithm. Right? It doesn't significantly impact the performance of the overall algorithm. Choosing a small mu would in fact ensure that in each round of the Newton's method, you don't take too many steps. So the inner iterations, so these are what I call the inner iterations. This is my inner loop, and this is my outer loop. Choosing a small mu ensures that the inner loop converges faster, but the outer loop takes much longer to converge, right? Because in some sense, we are taking very, very small steps towards the actual constraint minimum. And choosing a larger value of mu would ensure that the inner loop takes longer to converge, but the outer loop takes less time to converge because we are taking bigger steps in each row. Okay? So again, people usually choose mu kind of arbitrarily. If you know something more about the problem, then you can maybe more judiciously choose mu. But in many cases, it is not so crucial. You choose something that's slightly larger than mu and just be done with it. Okay. The third point is how do you choose the stopping condition? You should remember that at each step, we are actually not solving the actual optimization problem. Right? We're solving a different optimization problem, wherein we're minimizing t times f0 of x plus p of x. So in each outer iteration, we are trying to solve minimum x such that ax is equal to b of p times f0 of x plus p of x. Okay. And from this we are getting a solution which I call x star of t. So the natural question to ask is how far away is x star of t from the actual minimum? So how much does f of x star of t differ from f star, where f star is the actual constraint minimum? So this is the minimum of f0 of x subject to ax equal to b and fi of x less than or equal to 0 for all I. Right? The nice thing is that you can formally prove that for any t greater than 0, f of x star of t minus f star is always going to be less than or equal to m by t, where m is the number of inequality constraints that we have, and t is of course a parameter that we choose. So this is nice because if we know that Newton's method converges, then we know exactly how to choose this particular stopping condition. We know m, we know t, so you keep running this until m by t is less than or equal to epsilon. Right? Because you're guaranteed, I mean, could be better, could be much better than m by t, but for sure you know that it's going to be less than or equal to m by t. So this stopping condition is just m by t is less than or equal to epsilon. So as long as m by t is greater than epsilon, we keep running this. Okay? Any questions? Okay, so let's try to see how this works in practice. What do you mean what constraint do you want? Correct, I agree. That's true. So the overall Hessian would have to be positive definite. Remember, there is only one component, right? Because the overall Hessian, what would that be? That would be the Hessian of f0 of x plus, or t times the Hessian of f0 of x plus the Hessian of t of x. We want to make sure that this is invertible at every step. Sorry? Correct. The underlying assumption is that all of these, I mean, the overall matrix is full. The Hessian has to be full. Or in other words, it has to be positive definite. I don't care about the individual matrices themselves. Right? As long as the sum is positive definite, I am satisfied. Right? So that's an underlying assumption that I am making. And it doesn't work without that. Any questions? Okay, so let me use some of these things I had earlier. I'll try to solve the same problem as last time, least squares, but now I'm going to add another constraint. Let me say that I want to solve least squares with the constraint that the 2 norm is less than or equal to 1. Because 2 norm squared is less than or equal to 1. So let's write that down. The example that we are interested in is minimize let's say norm of ax minus b the whole square subject to the 2 norm of x square is less than or equal to 1. Is this a convex optimization problem? Yes? I don't hear a confident yes. If does A have to be positive semi-definite? I'm sorry? Okay. I want 2 norm of x the whole square is less than or equal to 1. That is, constraints are convex because I want fi of x less than or equal to 0 where each fi of x is convex. 2 norm of x the whole square is convex. What about the objective function? Correct? So this is the same as minimize. What does this expand to? X transpose AX A transpose A X minus 2 B transpose Ax plus P transpose B, subject to the constraint that X transpose X minus 1 is less than or equal to 0. Okay, let's compute. So now using Newton's method, what is P of X? What is gradient of f0 of X? Remember, this is my f0. What's the gradient? Two times Ax minus B the whole transpose. Okay, what's an easier way? A transpose Ax minus 2 times A transpose B. Right? What is the Hessian? This is 2 times A transpose A. Right? Okay, what about phi 0? Sorry, phi of x. What is the gradient of phi of x, which is, let me first write down what phi of x is. Phi of x is the negative, there's only one inequality constraint. So negative of log of minus x transpose x minus 1. Right? What is the gradient of P of x? You can as well choose minus log of 1 minus x transpose x. Minus okay, to identity matrix by minus 2x divided by 1 minus x transpose x. Are you sure about the sign? There's a negative sign here. So the gradient of log of 1 minus x transpose x would be 1 by 1 minus x transpose x times the gradient of 1 minus x transpose x, which is minus x. So minus of minus x would be, sorry, 2x, not minus x. Right? Plus, plus 2x. What about the Hessian of P of x? Yeah? Okay, so 2 times the identity matrix divided by 1 minus x transpose x minus 2 by 1 minus x transpose x the whole square times into minus 2 x xx transpose, right? Again, it's very similar to a standard calculus in one way, but you have to be careful about the dimensions. Right? Getting the transpose right is very important. Okay, so this is just 2 times the identity matrix divided by 1 minus x transpose x plus 2 times 4 times xx transpose divided by 1 minus x transpose x the whole square. Correct? Okay, so let's try to write this down. So what is the gradient of the overall function? It is equal to the grade of the new objective is basically 3 times gradient of h0 of x plus the gradient of phi of x. So let's write that up. So the inputs to this compute gradient are a, b, x, and now the t. Let me call this gradient of f0 gradient of phi. What is this equal to? This is equal to 2 times x divided by 1 minus x transpose x. 2 times x divided by 1 minus x transpose x. We want to return 3 times h0 plus gradient of okay. Fine. So this is the computation of the gradient. What about the Hessian? Now the Hessian would again involve a okay. So the Hessian of f0 is equal to just 2a transpose a. What is the Hessian of phi? 2I by 1 minus x transpose x of divided by 1 minus x transpose x plus 4xx transpose x here is a row vector, that's my input. So xx transpose divided by 1 minus x transpose x the whole square. So I want to return t times Hessian of f0 plus Hessian of sorry? Yes, that's okay. Python is going to take care of the row versus column. Okay. Yes. X is a row vector in this case. in case there's an error, we'll worry about it. Okay. So let's see, we want to compute the function, which is my f0. My p function is minus log of 1 minus x transpose x. One minus x transpose x, and I want to return p times f0 plus p. Okay, so far so good. So now I have computed the gradient, the Hessian, and the function. I have these helper functions that are going to do all of these. I can use this as a black box. Okay. Now let me just, I have set up the problem. So I will randomly generate a 5 by 3 matrix A, and B is something that's fixed here. This is my matrix. Okay, so now I can't start with an arbitrary initial point, right? Because it has to satisfy x transpose x is less than 1. So let me choose an initial point which is LP of random, and I will normalize this such that 0.1.1 times so normalize and multiply. So the norm of this initial point is 0.9. Okay. Now the optimum solution is no longer A transpose A whole inverse times A transpose B, because we now have a constrained optimization problem. But if you didn't have any constraints, let's see what the solution would have been. Right? So okay. Let's forget about this for now. I only care about the up to the actual unconstrained minimum has a norm of 2.5. So the constrained minimum is now definitely going to be different from the unconstrained minimum. Alright, let's try to first find the constrained minimum. CEX type, okay, which we can use as a black box. So how would I set this up? So I need to first define variables. So let me call x the variable of it's an n length vector. What is my objective? It's to minimize the norm, right, minimizing the two norm square or minimizing the two norm is one and the same. So just use this a times a times x minus b. What are the constraints? The two norm square or two norm x should be less than or equal to 1. Right? And I declare the problem, which is objective constraints. I'm sorry? X is, that's okay. I mean, MacMill is going to change the dimensions appropriately. I don't have to really worry about that. I'm not going to be very careful with that. Print MacMill something into X. Okay. Okay, so the minimizer happens to be this particular vector, and the norm of the minimizer is something very close to 1. So the minimum is achieved at a boundary point. So recall that the constraint set is a ball of radius 1, and the minimum is now being achieved somewhere on the surface of this ball of radius 1. Okay? There's no, it's not achieved at an interior point, which is exactly as we had expected. Suppose it didn't. Yes. Again, we're focusing only on convex optimization problems where there is a well-defined local minimum. Right. Under those assumptions, yes, either the global minimum is achieved at an interior point, or the constrained minimum is going to be achieved at a boundary point. One of those two things has to happen. I mean, it's intuitive, right? Okay, so now we know what the actual minimizer is. Let's try to solve this using Newton's method or the barrier method. So I'm going to copy the same function that we had in the previous class for Newton's algorithm. Okay, so this, I'm going to use this as a black box. So Newton's method is going to take as input A, B, an initial point, and T. I'm not going to change anything else from the previous thing, but I have to choose the T. The gradient vector also depends on T. So Hessian depends on A, B point, two. Vector, then use the same direction. Okay. Then let me also compute F0. So this constitutes the inner loop. Right? All of this, Newton's backtracking method, all of this would just constitute the inner loop. Now I need to write the outer loop. So quickly go back to the algorithm itself. I have to initialize some particular x that satisfies the constraints, and I need to fix mu, epsilon, and t. Right? T is equal to 1. I'm sorry, m is equal to 1, but I need to fix a particular t. Need to find method A, B, shift point. Fix and epsilon equal to 0.01, and I want mu. Let me fix this to be 1.5. I also have to fix a t, which is say 0.5. Fix current. So now I fixed an x which satisfies the constraints with strict inequality. Now I run Newton's method, right? As long as the stopping condition is not reached by m by t, 1 by t is less than is greater than epsilon, I also need the final x. Variant is equal to so let me also keep track of the loss and f0. Just an empty array, and I need to increment t times mu. Okay, question? Well, this is going to return an array. I need to concatenate the two, because otherwise it's going to be an array of arrays, which I don't want. I can also compute the final f0, which is the last, at the end of the Newton's method, whatever the f0 of it. Okay, let's see. So now I need to call barrier, the barrier method. I need to return something first. Zero array. have an error. So AX yeah. What we call this. Certificate. you what is wrong here. So 5 by 50. Same problem. Can we calculate the gradients correctly? It's b to x by 1 minus x squared. Yeah. Which one? This? Wasn't it a plus 4? It was plus 4. Okay. Yeah. Grad 5? Even here? I don't think so, because let's see. No, that doesn't change anything. No, there's something else that is wrong. of course, I'm assuming that the SCM is positive definite. Let me see. Yeah? Events below. What do you mean nested within? Correct. Okay. Okay. That's okay because this is only to compute the step size, right? This part is for the line search, so that is okay. Just run this. Okay, so the descent direction is always reasonable. What? Let me also see what the point is. Yeah. It does depend on initialization. But still it satisfies the constraints, right? Eventually it should converge. The only possible problem is that the step size I'm choosing is not correct enough. So I'm implementing it too fast. So let's choose something different. Yeah, so it is decreasing now, it's reasonable, but it seems to take longer to convert. So maybe I start with something that is close to 1, 1 by 7. Okay, but it's somehow not decreasing to the minimum value yet. Okay, so I guess this would require some debugging, but you get the idea behind this. There's probably something minor that's wrong with this code. Shouldn't be too hard to fix it. Any questions? Okay. So let's stop here. We will have the final exam, final test on Friday. You are allowed to bring a cheat sheet written on one side, and the syllabus is also mentioned in the class, in the classroom. Okay, so that will be the last lecture for this particular course. Maybe see you in another course next semester. Okay, so I just realized what the problem was.
Effectively, this solution, the exact solution, is obtained by solving an optimization problem in CVXPy. But recall that in CVXPy we wanted to minimize the 2 norm of ax minus b, not the 2 norm of ax minus b the whole square. So the actual solution is SOLN square. Yeah, so there's nothing wrong with the barrier function implementation itself, the barrier method implementation. It was just that I was not plotting the actual optimal value, and we see that the barrier method indeed does converge to the optimal value as the number of iteration increases.